The laws of physics shatter at the edge of a black hole. This is the enigmatic realm where time itself can stop and reality becomes stranger than fiction. We are about to explore 15 mind-bending paradoxes that pit Einstein's relativity against quantum mechanics, conflicts so deep they leave the greatest scientists searching for answers. By the end, you will grasp how these cosmic puzzles are forcing a total rewrite of our understanding of reality itself. We will see how information can vanish into nothingness and whether an astronaut is burned alive or passes through unscathed. Each paradox is a crack in the foundation of modern physics, and together they point toward a hidden truth about the universe. What do you think it means when our most trusted laws of nature simply break down? Stephen Hawking's brilliant calculations revealed something haunting. Black holes are not eternal. Over timescales so vast they dwarf the age of our universe, a black hole slowly leaks energy, fading away in a whisper of particles we call Hawking radiation. This is where our first great paradox takes root. Think of your life as a story written in the atoms of your body, in every memory and experience. That is information. The fundamental rules of quantum mechanics, the laws that govern the very small, state with absolute certainty that information can never be destroyed. It can be scrambled, hidden, transformed, but it must always, in principle, be recoverable. Now, take that story of you and toss it into a black hole. According to Hawking's original work, as the black hole radiates and eventually vanishes, all that unique information about you is lost forever, erased from the cosmos. It becomes pure, featureless energy. This creates an impossible conflict. On one side, quantum mechanics says information is sacred and permanent. On the other, Hawking's application of general relativity says black holes destroy it utterly. This is the black hole information paradox. It is as if the universe has two sets of rule books, and they give completely opposite answers to a basic question. Does reality have a permanent record, or does it allow for ultimate forgetting? The tension is so severe that it forced Hawking himself to famously make a bet, conceding decades later that information must somehow escape. But how? Perhaps the information is imprinted in subtle patterns on the Hawking radiation, a cosmic hologram. Or maybe it is preserved at the event horizon itself, a theory known as the Firewall Paradox, which we will come to shortly. This paradox is not just a philosophical puzzle. It is a glaring signal that our theory of gravity and our theory of the quantum world are incompatible. Resolving it may require a revolution, a theory of quantum gravity that weaves space and time from something deeper. The fate of information asks what the universe is ultimately made of, laws or chaos. And if information is preserved, what horrific price might be paid by anything trying to retrieve it? Yet this potential solution to the information paradox creates a terrifying new dilemma. Picture our astronaut having survived the long journey, now drifting toward the black hole's edge. According to Einstein's own principle, the event horizon should be an uneventful boundary. If the astronaut were to cross it, they should feel nothing at all, experiencing no sudden jolt, no dramatic signal. This is the cherished no-drama prediction of general relativity. But quantum mechanics, in its quest to save information, paints a horrifically different scene. To prevent information from being lost forever, some calculations suggest the horizon cannot be a placid place. Instead, it must be a chaotic barrier of unimaginable energy, a literal wall of fire made from every particle the black hole has ever consumed. This is the Firewall Paradox. In one moment, our astronaut is floating in empty space. In the next, they would be utterly vaporized by this sudden inferno. So which is it? Is the universe loyal to Einstein, offering a smooth, if one-way, passage? Or is it loyal to the quantum rulebook, demanding a violent, fiery end to protect cosmic data? This is not a minor disagreement. It forces physicists to choose between two pillars of modern science. The very existence of a firewall means that our intuitive idea of space as a smooth, continuous fabric breaks down completely at the quantum level. It suggests that locality, the principle that objects are only influenced by their immediate surroundings, might be an illusion. The dilemma connects to an even deeper mystery, one that lies at the very heart of the darkness. What actually happens at the center of a black hole, where all paths and all paradoxes ultimately lead? All paths lead to a single point of infinite mystery. Deep within the black hole, beyond the event horizon and any potential firewall, lies the ultimate destination and the ultimate paradox. General relativity, in its elegant equations, predicts that all the matter that ever fell in is crushed into a point of zero volume and infinite density. This is the singularity. Here, the very fabric of spacetime curves to a breaking point. Gravity becomes so strong that the concepts of here and there, before and after, simply cease to have meaning. Our most trusted map of reality tears apart. The singularity is a paradox because infinity is not a physical answer. It is a mathematical scream that our theory has failed. It tells us that at the most extreme edge of nature, our understanding hits a wall. The universe appears to allow a place where the rules of cause and effect, the very predictability that physics is built upon, breaks down entirely. What happens at the singularity? The equations give no answer, only an error message written in the language of infinity. This challenges a core belief of classical physics, that if you know the state of a system completely, you can predict its future. The singularity is a place of ultimate unpredictability. It is as if you followed a road map perfectly, only for the map to end at a cliff edge with a sign that reads, "Beyond this point, destinations are unknown." Some theories, like loop quantum gravity, propose a way out of this conundrum. They suggest that the crushing gravitational collapse does not continue forever. Instead, at the tiniest possible scale, the fabric of spacetime itself has a granular structure, like the pixels on a screen. This could cause the collapse to rebound, like a cosmic bounce, transforming the black hole singularity into a moment of explosive new creation. Yet, even if this is true, a profound question remains. The singularity, or whatever replaces it, is locked behind the event horizon, a curtain that no signal from within can ever pierce. Does this mean it represents the absolute limit of what we can ever know, a permanent blind spot in our cosmic vision? Or is that curtain not a wall, but a gateway? If the crushing gravity of a singularity can warp space and time beyond recognition, could it warp them into something entirely new, a bridge to another reality altogether? This idea pulls us toward one of the most speculative and captivating possibilities in all of cosmology. The equations of general relativity are perfectly symmetrical with respect to time. Run them forward and you get a black hole, a cosmic drain. Run them backward and you get its bizarre mathematical twin, a white hole. This is a region of spacetime where nothing can ever enter, only erupt outward in a relentless cosmic geyser of matter and energy. The white hole paradox asks a simple, haunting question. If the math so elegantly allows it, why does our universe seem to contain only drains and never fountains? On paper, a white hole is a valid solution, a beautiful mirror image. Yet in reality, it appears to be forbidden. It seems to violate a fundamental cosmic rule, the second law of thermodynamics, which states that disorder, or entropy, always increases. A white hole spewing out perfectly ordered material from nowhere would essentially be a machine for decreasing entropy, a cosmic rewinding of the tape that nature itself seems to reject. This creates a profound tension between the cold beauty of mathematics and the messy, one-way flow of physical reality we observe. Some theorists propose a fascinating resolution, a cosmic metamorphosis. Perhaps when a black hole evaporates via Hawking radiation and shrinks to a microscopic size, quantum gravity effects could cause it to rebound, not into a singularity, but into a white hole. In this view, the black holes we see in the cosmos are not eternal prisons, but merely in a long-lived state of collapse. Their eventual fate, after timescales longer than the current age of the universe, could be to turn inside out and become these explosive exits. This would be a spectacular, if unimaginably delayed, release for all the information ever swallowed. It offers a potential escape route from the information paradox, a backdoor written into the fabric of spacetime itself. Yet, for all its theoretical elegance, we have never seen one. No telescope has ever caught a white hole in the act of its impossible eruption. This leaves us at a crossroads. Are white holes purely mathematical ghosts, artifacts of a theory pushed beyond its limits? Or are they real, hidden in plain sight, perhaps masquerading as certain inexplicable, high-energy explosions in the distant cosmos? Contemplating these theoretical exits forces us to confront the one-way arrow of time in our universe. And if such an exit can exist, could it be connected to an entrance somewhere else, forming not just a hole but a tunnel? This elegant tunnel through spacetime presents a paradox of its own. Wormholes, often called Einstein-Rosen bridges, are not science fiction but legitimate solutions to the equations of general relativity. They are theoretical shortcuts, a cosmic fold connecting two distant points in space, or perhaps even the fabric of different universes altogether. The paradox emerges not from their existence on paper, but from their stability in reality. For a human or even a photon to safely traverse this bridge, the throat of the wormhole must be held open against the immense force of gravity that wants to snap it shut instantly. Keeping it open requires something truly bizarre, exotic matter. This is not just strange matter, but matter that possesses negative energy density, effectively creating a kind of anti-gravity to prop the tunnel open. Here lies the first layer of the paradox. Our entire understanding of physics, from the classical to the quantum, suggests that such exotic matter, if it can exist at all, exists only in vanishingly small amounts. To stabilize a wormhole large enough to walk through would require astronomical quantities of this phantom substance, so the universe's rulebook seems to offer a blueprint for a cosmic subway system, but then hides all the necessary building materials. Yet the paradox deepens far beyond mere engineering. If a stable wormhole could somehow be created, it would shatter our understanding of cause and effect. Imagine one end of the wormhole is placed on a spaceship traveling at near light speed, while the other remains stationary. Due to time dilation, time would pass more slowly for the moving end. This would not just connect 2 points in space, but 2 different moments in time. You could potentially step into the stationary end and exit the moving end in your own past. This creates the potential for classic time travel paradoxes, where you could prevent your own journey, creating a logical loop with no beginning. The wormhole paradox, therefore, forces a profound question. Does the universe inherently forbid such shortcuts, not because the math is wrong, but to protect the chronological order of events, the very foundation of reality as we experience it? Or does it merely place them beyond the reach of any known civilization, a secret of spacetime reserved for entities of unimaginable advancement? This challenge to cause and effect leads us directly to a related and even more mind-bending consequence of warped time, one that seems to grant a form of immortality, but at a terrible cosmic price. Gravity does not just bend space, it twists time itself. This is the unsettling reality of gravitational time dilation, a prediction of Einstein's relativity that becomes a profound paradox at the edge of a black hole. Think of it as the universe's most extreme clock experiment. Two identical twins embark on a cosmic journey. One twin remains in the safety of a distant spacecraft, while the other, brave and curious, journeys toward the black hole's event horizon. To the watching twin, something deeply strange occurs. As the falling sibling approaches that ultimate boundary, their signals back home begin to stretch and slow. Their movements, captured by the spacecraft's cameras, appear to crawl. Their heartbeat, if it could be monitored, would seem to draw out into a deep, slow thrum. At the very threshold of the horizon, from the distant twins' perspective, the falling twins' time appears to grind to a complete and eternal halt. They are frozen there, a statue against the dark, never quite crossing, their final moment stretched across infinity. But here is the paradox. For the twin who is actually falling, none of this slow-motion drama is happening. In their own frame of reference, time passes at its normal, familiar rate. They feel the acceleration, they see the warped starlight, but their watch ticks forward second by second. They crosses the event horizon in a finite amount of their own personal time, feeling no sudden jolt, no magical barrier. So we are left with an impossible question: who is experiencing the true reality? From the outside, the twin never crosses. From the inside, they cross without incident. Both perspectives are equally valid according to the laws of physics. This is the relativity of simultaneity in its most extreme form. The idea of now, of a single universal present, completely shatters. There is no cosmic clock that can reconcile these two experiences. The event horizon, therefore, is not just a physical location. It is a perceptual boundary, a line beyond which the shared story of the universe splits into irreconcilable narratives. This forces a deeply philosophical dilemma. Is the horizon a real physical wall, or is it an illusion created by our limited, distant perspective? If we insist that the frozen image from outside is the ultimate truth, then what becomes of the falling twins' direct experience? Is it less real? Physics must account for both stories, and this paradox suggests that reality itself is observer-dependent. The black hole does not have one history, but many, woven together by the threads of different viewpoints. This relativistic weirdness is not just a curiosity. It is intimately tied to the black hole's most defining feature, its darkness. The light from the falling twin becomes infinitely redshifted, stretched to wavelengths beyond detection, carrying less and less information until it effectively winks out. This loss of signal is what creates the illusion of a frozen surface. The paradox of time dilation and the paradox of lost information are two sides of the same deeply warped coin. And if time can be stretched to a standstill, what does that imply for the fate of all the matter that has ever fallen in? Could it be that from a certain point of view, the entire history of a black hole's consumption is smeared across its surface, a cosmic painting of everything it has ever absorbed? Light itself can become trapped in a cage of pure gravity. Just beyond the point of no return, surrounding the event horizon, lies a region of space so warped that the very paths light travels are bent into perfect circles. This is the photon sphere. Here, gravity's grip is so precise, so overpowering that photons, the particles of light, can orbit the black hole endlessly, like cars on a circular track with no exit. This creates a visual paradox that defies all everyday experience. If you could somehow hover safely within this sphere, you would witness the impossible. Light from the back of your own head could travel all the way around the black hole and return to your eyes. You would see yourself from behind in real time, a ghostly afterimage orbiting in the darkness. In theory, you could see multiple copies of yourself, each fainter, as light makes 2, 3, or even more laps before finally reaching you. It is a hall of mirrors crafted not from glass, but from the sheer curvature of spacetime itself. Yet this mesmerizing optical illusion is profoundly unstable. The photon sphere is a knife's edge. the difference between an eternal orbit and a fatal plunge is unimaginably tiny. The slightest nudge, the most minuscule perturbation, would send a photon spiraling down into the black hole's depths or flying out into the wider universe. Nothing can truly remain there, not even light. This instability presents a deep informational paradox. What would it mean to have a region of space where information carried by light could theoretically loop back on itself forever? For a distant observer trying to image a black hole like the Event Horizon Telescope, this sphere is the source of the bright ring of light we see, the final orbit before darkness. But for communication, it represents a cosmic dead end. Any signal sent along such a path would be trapped in a closed loop, echoing upon itself until it faded or was disrupted. It could not carry a message out, only revolve in a silent, endless dance. This challenges our most basic assumptions about how information moves through the universe. We think of light as the ultimate messenger, traveling in straight lines or at least predictable curves. But here, gravity writes its own rules, creating short circuits in the fabric of reality. The photon sphere is not a channel for communication, but a gravitational echo chamber, a place where information goes to orbit, not to travel. It asks us whether the universe allows for perfect, closed loops of cause and effect, or if instability is a fundamental law that prevents such logical knots from forming. If matter and light behave so strangely in this region, what then becomes of something more substantial, like a star venturing too close? The fate that awaits is not a quiet orbit, but a violent and spectacular unraveling, a process that stretches the very concept of an object to its breaking point. Spaghettification is a cosmic horror story told by gravity. An astronaut, a spaceship, or even an entire star drifting too close to a black hole will not simply be crushed. Instead, the difference in gravitational pull between the head and the feet becomes so monstrously powerful that the object is stretched into a long, thin strand of its former self, like cosmic taffy. This is a purely classical prediction, a brutal yet straightforward consequence of Einstein's gravity. But introduce the quantum world, and this violent stretching warps into a profound paradox. At the quantum level, particles are not tiny billiard balls. They are described by wave functions, clouds of probability that define where a particle is likely to be found. These wave functions can, in theory, be stretched and spread out across vast distances. So what happens when the wave function of an electron in your body is pulled from your head to your feet over a distance of thousands of kilometers? Does it remain a single, coherent quantum entity, or does it shatter? This is the Spaghettification Paradox. It forces us to ask whether the extreme tidal forces of a black hole don't just destroy an object's form, but also erase its quantum identity. Quantum information relies on delicate relationships, on entanglement and precise phases. Stretching a wave function over such an immense scale could scramble these relationships beyond recovery, effectively decohering the quantum state. It would be like taking a beautifully complex symphony and stretching the recording over a century until every note is isolated and the music is lost, leaving only noise. In this view, spaghettification is not just a physical transformation, it is an informational massacre. Yet, quantum mechanics is notoriously resilient. Some theories suggest the information might not be destroyed, but rather encoded in a new, horrifically distorted way. Perhaps the stretched strand becomes a one-dimensional quantum record, a filament where all the original data is still present, just written in a language of extreme tension and strain. The paradox sits at the violent intersection of two worlds. Classical gravity sees a noodle. Quantum physics sees a wave function undergoing impossible stress. Reconciling them requires understanding how locality, the idea that things only interact with their immediate neighbors, survives when those neighbors are pulled light years apart. Does an object's identity dissolve in this process, or is it merely translated into a form we cannot yet comprehend? This question of preservation amidst distortion leads us to an even more fundamental warping, one that affects not just matter, but the empty space it moves through. A black hole is not just a cosmic vacuum, it is the universe's most chaotic filing cabinet. This is the ninth paradox, where the relentless flow of time and the concept of disorder collide. Physicists Jacob Bekenstein and Stephen Hawking made a startling discovery. Black holes possess entropy, a measure of their internal disorder, and it is astronomically large. Their formula directly links this entropy to the surface area of the event horizon. The bigger the black hole, the more area it has and the more chaos it contains. This was a revolutionary idea, suggesting that a black hole is not a simple, featureless pit, but rather the most disordered object possible, a thermos bottle holding the ultimate cosmic mess. Yet this creates a baffling contradiction. Remember the twin paradox where time grinds to a halt at the horizon from an outside view. Gravitational time dilation doesn't just slow clocks, it stretches light to lower energies, a phenomenon called redshift. From our distant perspective, all the furious motion and collisions of matter falling into the black hole appear to slow down and freeze. The energy states become so redshifted they fade from view entirely. So we have a system that, from our vantage point, looks completely static and frozen. Yet we are told it contains the highest possible entropy, a state we normally associate with frenetic, dynamic motion, like the constant churning of molecules in a hot gas. How can something that appears perfectly still be the epitome of disorder? This is the gravitational time dilation entropy paradox. It forces us to reconsider what entropy even means in the grip of such extreme gravity. Our classic textbook definition, tied to heat and motion, utterly fails here. The resolution may lie in where we think the entropy is located. Perhaps the disorder is not inside the black hole at all, in any traditional sense. The holographic principle suggests that all the information describing the black hole's contents, and thus all its entropy, is not smeared throughout its volume, but is instead encoded on its two-dimensional surface, the event horizon. In this view, the frozen image we see from outside is not an illusion, it is the entire story. The horizon is a bustling, chaotic screen, a pixelated display where each tiny plank-sized area holds a bit of information. The entropy is in the astronomical number of ways those pixels can be arranged to describe what fell in. The internal chaos is projected onto a still surface, resolving the paradox of a dynamic disorder appearing frozen. This holographic idea transforms the black hole from a three-dimensional prison into a two-dimensional painting of everything it consumed. And if the surface holds all the information, then the slow evaporation predicted by Hawking radiation is not a destruction of data, but a careful, pixel-by-pixel release of that stored story back into the universe. This thermodynamic puzzle is not just about black holes, it is a clue about the fundamental nature of reality itself, suggesting that space, time, and information are woven together in ways we are only beginning to decipher. Hawking radiation presents a final, exquisite contradiction. It offers a way for black holes to fade from existence, yet in doing so, it threatens the very logic of quantum theory. The process must be unitary, a fundamental rule stating that the evolution of any quantum system is perfectly reversible. If you know the final state of an evaporated black hole, you should, in principle, be able to rewind the cosmic tape and reconstruct exactly what fell in. But Hawking's own math painted a different picture. He showed the radiation leaking out would be purely thermal, like the glow from a hot stove, random and featureless. It would carry no fingerprints, no hidden code of its origin. This creates the Unitarity Paradox, a direct clash between two non-negotiable demands. The black hole must vanish to satisfy thermodynamics, but its disappearance must not erase the quantum story of the universe. It is as if a magnificent library were set to slowly burn, and the only smoke rising was blank gray and identical no matter what books were inside. The information would be gone, violating the core quantum commandment that it must live forever. For decades, this seemed an insurmountable wall. Then came a glimmer of resolution from the holographic principle, embodied in the Page curve, named after physicist Don Page. This idea suggests that information does not stay locked inside. Instead, it begins to leak out in the radiation much earlier than anyone thought, but in a subtle, scrambled way. The radiation only appears random at first. As the black hole evaporates past its halfway point, the outgoing particles become intricately entangled with the radiation that left earlier, weaving a complex quantum tapestry that secretly encodes everything that was lost. The event horizon becomes a furious processor, not a wall, performing the ultimate computation to translate three-dimensional collapse into a two-dimensional data stream. This process forces physics to confront a staggering idea. For information to escape in this manner, the principle of locality, the notion that things only influence their immediate neighbors, must break down at a fundamental level. The particles leaving the horizon must somehow be connected to the interior they left behind, a connection that defies our classical understanding of space. So the paradox pushes us toward a universe where space itself, and the separations it creates, may be an emergent illusion from a deeper, interconnected quantum reality. And this leads to a tantalizing, if distant, thought. If this radiation truly carries the signature of all that was consumed, could we ever build a receiver to decode it? Imagine a far future civilization surrounding a dying black hole, collecting every last particle of Hawking radiation in vast energy nets. In theory, with a quantum computer of unimaginable power, they could run the tape backwards. They could unscramble the signal and witness in perfect detail the history of everything that ever fell into that darkness. They would see the ancient stars, the rogue planets, perhaps even the fate of long-lost explorers. The black hole would not be a tomb but a time capsule, its contents broadcast in a final burst of light as it winks out of existence. This possibility transforms the paradox from a crisis into a promise, a hint that nothing in the cosmos is ever truly forgotten, only transformed. The mirror reflects the whisper, and the whisper becomes a scream. This is the terrifying elegance of the black hole bomb paradox. We know a rotating black hole can amplify certain waves through a process called superradiance, stealing a tiny fraction of its rotational energy. Now imagine constructing a perfect, indestructible sphere of mirrors around such a black hole, trapping it completely. The faint Hawking radiation, those quantum particles born at the event horizon, would now be caught inside this cosmic cavity. Each time a particle reflects off the mirror and falls back toward the black hole, the rotational energy can amplify it slightly. The particle gains energy, bounces off the mirror again, and returns to be amplified even more. In a perfect theoretical scenario, this creates a runaway feedback loop, a chain reaction of energy extraction that grows exponentially until the mirrors shatter in a cataclysmic release. The paradox is one of sheer potential. Could this process extract more energy from the black hole's spin than thermodynamics should allow? It appears to offer a way to drain a black hole's rotation with near-perfect efficiency, a cosmic engine of unimaginable power. The mathematics suggests it is possible, yet the universe seems to have a deep aversion to such infinite or runaway processes. Nature likely has a built-in fuse. Imperfections in any real mirror, or the black hole's own gravitational influence, would probably disrupt the perfect resonance before the explosion becomes infinite. But the thought experiment forces a profound shift in perspective. It transforms a black hole from a passive consumer into a potential power source, a battery locked in gravity's vault. This leads to a speculative, almost science-fictional question. Could a sufficiently advanced civilization ever build such a structure, not as a bomb, but as the ultimate power plant? The energy yields would dwarf every star in a galaxy. It blends the hardest astrophysics with the furthest edges of engineering imagination, asking if the laws of physics themselves place a limit on how much energy can ever be taken from a spinning hole. Yet to even contemplate such control, one must assume the universe near a black hole behaves in a predictable, deterministic way. But what if, at the quantum level, it does not? What if the very act of trying to measure or harness this energy changes the outcome in fundamentally unpredictable ways? Determinism, the clockwork universe where every effect follows a known cause, meets its final breakdown deep within a spinning black hole. Past the event horizon of a rotating Kerr black hole, the mathematics of general relativity reveals another boundary, a Cauchy horizon. This is not a wall of matter, but a frontier of predictability. In our everyday world, if you know the exact position and momentum of every particle in a system, classical physics suggests you can calculate its future state with perfect accuracy. The Cauchy horizon shatters this comforting idea. It is a mathematical boundary where the equations of general relativity themselves become unsolvable. The smooth fabric of spacetime, which allows us to trace world lines from the past into the future, develops rips and tears. Beyond this point, the future is not merely unknown, it is mathematically undefined. You could have two identical universes with identical histories up to that precise boundary, and they could evolve in completely different, unpredictable ways afterward. The universe's own rulebook offers no guidance for what happens next. This is the profound challenge of the Cauchy horizon paradox. It suggests that inside a black hole, the very concept of cause and effect may dissolve into nonsense. The deterministic worldview, a pillar of science since Newton, hits a wall of pure mathematical chaos, and this chaos may not be quiet. When quantum effects are considered, the situation becomes even more extreme. The region around the Cauchy horizon might concentrate an infinite amount of energy, creating a wall of instability sometimes called mass inflation. This is not a solid object, but a storm of gravitational and quantum fury so intense it could act like a second singularity, a barrier of pure unpredictability. So we face a deep question. Is the interior of a black hole a realm of true randomness, a place where the universe's laws simply cease to govern? Or does this paradox, like the singularity itself, simply signal that our current theories are incomplete? The hope is that a theory of quantum gravity, which weaves the rules of the very small into the fabric of spacetime, might smooth out this infinite instability and restore a form of order we cannot yet imagine. This touches the very limits of scientific prediction. It asks whether some domains of reality are fundamentally unknowable, not because of our technological limitations, but because the universe itself does not define an outcome there. As we stare into this abyss of failed equations, we find it eerily mirrors another moment where all predictability vanishes, a moment not of collapse but of creation. The infant universe was a seething ocean of energy and possibility. In its first chaotic moments, regions of slightly higher density could have collapsed under their own weight, not into stars but directly into black holes. These are primordial black holes, fossils from the cosmos's very first second. They present a beautiful and frustrating paradox. On one hand, they offer an elegant candidate for dark matter, the invisible substance that holds galaxies together. A vast population of these ancient, drifting black holes could explain the gravitational glue we observe but cannot see. The paradox emerges from their lifespan. Hawking radiation tells us that small black holes evaporate quickly. A primordial black hole with the mass of a small mountain would have already vanished in a flash of gamma rays long ago. So, to still exist today, they must be either very small and evaporating right now, or very large and stable. Here is where observation clashes with theory. We have powerful telescopes scanning the sky for the telltale gamma-ray bursts of evaporating black holes. We see nothing like the expected signal. If they are too massive to evaporate, we should detect their gravitational influence, bending light from distant stars in specific ways we have not found. They are theoretically perfect, yet observationally ghostly. This is the primordial black hole paradox. Their elusive nature forces a difficult choice. Perhaps our models of the early universe are wrong, and conditions never allowed for their widespread formation. Or perhaps dark matter is something else entirely, and these cosmic relics are rarer than we hoped. This paradox ties the fate of black holes directly to the origin and composition of the entire cosmos. It suggests that the answer to one of our greatest mysteries, dark matter, might be written in the quantum fluctuations of the universe's first breath. And if the beginning holds such secrets, what does it imply for the ultimate end? Could black holes in their final act not just fade away but trigger a cosmic reset? The final whisper of a black hole presents a choice with no comfortable answer. After an eon of slow evaporation, after the last particle of Hawking radiation has drifted into the void, what remains? Two stark possibilities emerge, and both lead to profound contradictions. In one scenario, the black hole vanishes completely, leaving behind nothing but empty, featureless space. This clean ending, however, resurrects the original information paradox in its most acute form. If the whole and everything inside it simply cease to exist, then the universe has allowed a permanent erasure of data, violating the quantum rulebook at the very last moment. The alternative is just as troubling. Perhaps the evaporation stops at the smallest possible scale, leaving behind a stable, indestructible remnant no larger than the Planck length, a billionth of a billionth of a billionth of a centimeter. This speck would be the final tombstone for all the information the black hole ever swallowed. But here lies the paradox. To contain the informational history of entire stars, planets, and perhaps civilizations, this minuscule object would need a nearly infinite entropy density. It would be a cosmic knot of information so tight it defies any understanding of matter and energy. Such an object could be fundamentally unstable, or it might interact with the universe in strange, unpredictable ways, becoming a permanent source of potential chaos. This final state paradox forces us to confront the fabric of reality at its most fundamental level. It suggests that spacetime itself may not be smooth and continuous, but granular, like the pixels on a screen. The remnant would not exist within space, but would be a knot in the very weave of spacetime, a topological defect where information is stored not in matter, but in the shape of the universe itself. This aligns with the holographic principle, where the three-dimensional history of the black hole is encoded on a two-dimensional surface. In its final moments, the evaporating black hole could shed its mass but preserve its information as a holographic fossil, a persistent imprint on the quantum geometry of the vacuum. The end game of a black hole, therefore, is not just a physical process but a metaphysical one. It asks whether information is more fundamental than space and time. Can reality forget, or is every event, every particle, every story etched permanently into the cosmos, even if only as a ghostly pattern in the void? This ultimate question about memory and existence leads us to the final and most encompassing paradox of all, one that challenges the very nature of what is real. The universe might be the grandest illusion of all. This final paradox emerges not from a conflict between theories, but from a breathtaking proposal that could resolve them all. It is called the holographic principle, and it begins with a startling claim about black holes. The information for every star, every planet, every atom that ever fell into the darkness is not lost within a three-dimensional volume. Instead, it is painted like a cosmic tattoo onto the two-dimensional surface of the event horizon. The black hole's entire interior reality is encoded on its boundary, just as a three-dimensional image emerges from the flat, patterned surface of a credit card hologram. This solves the information paradox elegantly, for if the data is on the surface, it can slowly leak out via Hawking radiation as that surface evaporates. But the principle presents a paradox far deeper than any engineering puzzle. It asks a fundamental question about the nature of our own reality. How can a rich, three-dimensional world, full of depth and movement, be perfectly described by information confined to a two-dimensional screen? This challenges our most basic sensory experience. We live in a world of volume, of inside and outside. The holographic principle suggests this volume, this spaciousness, might be an emergent illusion. The true workings of the universe, including gravity itself, might be a shadow play projected from a simpler, flatter realm of information. Think of a movie. The experience is three-dimensional, with characters moving through landscapes with depth and time. Yet all that complexity is stored on a flat, two-dimensional strip of film, or as digital code on a drive. The holographic universe proposes that spacetime itself is the movie, and the quantum information on its boundary is the film. This idea stretches our intuition to the breaking point. If true, it means a black hole is not an anomaly. It is a Rosetta Stone. Its event horizon is the clearest example of this cosmic encoding, forcing physicists to see that all of space, everywhere, might operate by the same rules. The principle offers a potential path to unify gravity and quantum mechanics, not by forcing them together in three dimensions, but by showing that gravity itself is a consequence of quantum information interacting on a distant, lower-dimensional surface. Yet this beautiful, radical idea leads to a dizzying philosophical cliff edge. If our perceived reality, with its solidity and separation, is a projected illusion from a more fundamental flat reality, what does that imply for our own existence? Are our choices, our consciousness, our sense of free will also part of this grand projection? Are we, in essence, living inside a computation happening on the edge of the observable universe? The holographic principle paradox does not offer easy answers. Instead, it prepares us for a final synthesis, a moment to step back and see how these 15 mind-bending threads weave together into a single, startling tapestry of understanding. These 15 paradoxes are not isolated puzzles. They are a single, resounding message from the cosmos. Each one, from the frozen twin to the holographic screen, is a fracture in the elegant but incomplete map of reality we have drawn. They are not failures of science, but its most vital signposts, pointing toward a hidden landscape we are only beginning to perceive. The common thread is a profound truth. Black holes are not just objects in space. They are cosmic interrogation chambers, forcing our theories of the very large and the very small to answer for their contradictions. Every paradox, whether about lost information or warped causality, is a direct challenge. It tells us that general relativity and quantum mechanics, each magnificent in its own domain, are merely chapters in a grander story we have not yet finished writing. The promised framework of quantum gravity is not just an academic goal. It is the universe's own instruction manual, waiting to be decoded from the very distortions black holes create. This journey forces a radical rethinking of concepts we take for granted. Time is not a universal river, but a personal experience that can stretch to a standstill. Causality, the bedrock of logic, can twist into loops within a wormhole or shatter at a Cauchy horizon. Information, the essence of identity and history, may be more fundamental than matter itself, etched onto a two-dimensional boundary from which our three-dimensional world emerges. The implication is staggering. Reality as we perceive it, with its solidity and separation, might be a magnificent illusion, a projection from a simpler, stranger realm. This is not just physics, it is a philosophical revolution. It touches questions about the nature of existence, the limits of knowledge, and whether the universe is, at its heart, a vast computation of relationships. It even humbly suggests that our own consciousness, our sense of a continuous self moving through time, might be part of this emergent cosmic narrative. Yet this is not a story of helpless wonder, it is a call to exploration. Each paradox is a precise question, and for the first time in history, we are building tools to seek answers. The Event Horizon Telescope, which gave us that first ghostly image of shadow and light, is just the beginning. Future observatories, both on Earth and in space, will listen for the gravitational wave echoes of collisions, analyze the flicker of matter at the precipice, and hunt for the subtle signatures of Hawking radiation or primordial black holes. We are no longer just thinking about these mysteries, we are beginning to witness them. The data flowing in may soon provide the crucial clue, the unexpected observation that forces a new synthesis. A single anomaly in the ring of light around a black hole, a strange pattern in the evaporation of a tiny, lab-created analog, could be the key that unlocks quantum gravity. So we stand at a remarkable threshold. The paradoxes of black holes have dismantled our old certainties, not to leave us in confusion, but to clear the ground for a deeper understanding. They teach a vital lesson in humility, reminding us that the universe is under no obligation to conform to our intuition, but they also ignite an unparalleled curiosity. Every crack in our current theories is a window into a more profound truth. The journey through these 15 mind-bending ideas reveals that the greatest purpose of a black hole may not be to consume light, but to illuminate the profound and beautiful strangeness of reality itself. The landscape of these paradoxes reveals a universe far stranger than we ever dreamed. We have walked the edge where time grinds to a halt for an outside observer, yet flows normally for someone falling in. We have seen how information teeters between being permanently lost and eternally preserved, and how reality itself might be a grand projection from a simpler, flatter realm. These contradictions are not failures of science, they are its most brilliant beacons, each one a glaring signal that our current maps are incomplete, guiding us toward a deeper, more unified truth. They remind us that the cosmos is under no obligation to make sense to our human-scale intuition. The very fact that black holes exist, and that our theories break down when trying to describe them, is a gift. It is the universe's way of pointing toward the next great frontier. Every paradox, from the haunting silence of the information lost to the explosive potential of the black hole bomb, is an open invitation. An invitation to question our most basic assumptions, to explore the mathematics of the impossible, and above all, to marvel at the profound mystery woven into the fabric of existence. So the next time you look up at the night sky, consider this: within those points of perfect darkness, within the silent hearts of galaxies, lie not just cosmic vacuums, but the most powerful engines of discovery we have ever known. They hold the keys to questions about time, cause and effect, and the very nature of reality itself. Our journey through these 15 mind-bending ideas is just the beginning. Which of these paradoxes boggles your mind the most? Was it the frozen astronaut, the holographic universe, or the terrifying possibility of a firewall? Share your thoughts in the comments below. If you want to join us for more deep dives into the wonders of the cosmos, be sure to subscribe and hit the bell so you never miss an exploration. Keep questioning, keep looking up, and until next time, stay curious.